Earthquakes. These natural phenomena remind us that our planet is a dynamic and ever-changing place. They are powerful events, capable of causing widespread destruction and altering landscapes in an instant. But what exactly are earthquakes, and how do they happen? Imagine the Earth as a giant jigsaw puzzle with massive pieces called tectonic plates constantly shifting and grinding against each other. These plates, which make up the Earth's outer layer, are in constant motion, albeit very slow. The movement is driven by the intense heat deep within the Earth's core. As these plates move, they can get stuck at their edges due to friction. Over time, the pressure builds up until it exceeds the strength of the rocks holding the plates together. The result is a sudden release of energy in the form of seismic waves that travel through the Earth. This is what we experience as an earthquake. Understanding earthquakes is crucial for our safety and well-being. By learning about their causes, characteristics, and potential impacts, we can better prepare for these events and mitigate their devastating effects. To understand earthquakes, we must first delve into the Earth's interior. Beneath the Earth's crust, the planet's outermost layer, lies the mantle, a thick layer of hot, dense rock. The mantle is not solid but behaves like a very viscous fluid over long periods. Within the mantle, heat from the Earth's core creates convection currents. These currents are similar to the movement of boiling water in a pot, with hotter material rising and cooler material sinking. This continuous churning motion exerts tremendous force on the tectonic plates above. The interaction between the mantle's convection currents and the overlying tectonic plates is the driving force behind earthquakes. As the plates are pushed and pulled by these currents, they collide, separate, or slide past each other, leading to the buildup of stress along their boundaries. These plate boundaries, marked by fault lines, are the most seismically active regions on Earth. It is along these fault lines that the majority of earthquakes occur as the plates try to move past each other. Not all areas on Earth are equally prone to earthquakes. The Earth's tectonic plates meet at three main types of boundaries: convergent, divergent, and transform boundaries. Each type of boundary is associated with different types of earthquakes and levels of seismic activity. Convergent boundaries are where tectonic plates collide head-on. These collisions are responsible for some of the most powerful earthquakes on Earth, as well as the formation of mountain ranges and volcanoes. The Himalayas, for example, are the result of the ongoing collision between the Indian and Eurasian plates. Divergent boundaries are where tectonic plates move apart from each other. These boundaries are typically found on the ocean floor, where new crust is formed as magma rises from the mantle to fill the gap. Earthquakes at divergent boundaries tend to be less intense than those at convergent boundaries. Transform boundaries are where tectonic plates slide horizontally past each other. The San Andreas Fault in California is a well-known example of a transform boundary. The friction between the plates along these boundaries can cause significant earthquakes. Earthquakes are inherently unpredictable events. While scientists have made significant progress in understanding the processes that cause earthquakes and identifying areas at high risk, predicting the exact time, location, and magnitude of an earthquake remains a challenge. The Earth's crust is a complex and dynamic system, with countless factors influencing earthquake activity. The movement of tectonic plates, the buildup of stress along fault lines, and the composition of rocks all play a role in determining when and where an earthquake will occur. Despite the challenges, scientists continue to develop and refine earthquake forecasting models. By analyzing historical earthquake data, monitoring ground deformation, and studying changes in groundwater levels, they can provide probabilistic estimates of earthquake likelihood over specific time periods. However, it is essential to remember that these forecasts are not predictions. They provide valuable information for preparedness efforts but cannot pinpoint the exact timing or location of an earthquake. Section 5. Primary waves, the first tremors. When an earthquake occurs, it releases energy in the form of seismic waves that travel through the Earth. These waves are what cause the ground to shake and are responsible for the destructive effects of earthquakes. Two main types of waves are generated by earthquakes: primary waves, or P waves, and secondary waves, or S waves. P waves are the fastest seismic waves and are the first to arrive at a seismograph station after an earthquake. These waves travel through the Earth's interior, compressing and expanding the rocks in the direction of wave propagation. Imagine stretching a slinky and then letting go. The compression and expansion of the slinky are similar to how P waves travel. P waves can travel through solids, liquids, and gases, which is why they are used to study the Earth's interior structure. They are also less destructive than S waves because they cause less ground movement. Section 6. Secondary waves, the ground's dance. S waves are slower than P waves and arrive at a seismograph station after the P waves. Unlike P waves, which cause the ground to move back and forth in the direction of wave propagation, S waves cause the ground to move up and down or side to side, perpendicular to the direction of wave propagation. Imagine shaking a rope tied to a wall. The up and down or side to side motion of the rope is similar to how S waves travel. S waves can only travel through solids, not liquids or gases. S waves are more destructive than P waves because they cause more significant ground movement. The shaking motion caused by S waves can damage buildings, bridges, and other structures, leading to widespread destruction. Section 7. The Chilean earthquake of 1960, a record-breaking quake. The greatest earthquake ever recorded based on its magnitude occurred on May 22, 1960, near Valdivia, Chile. This colossal earthquake, known as the Great Chilean Earthquake or the 1960 Valdivia earthquake, had a magnitude of 9.5 on the moment magnitude scale, making it the most powerful earthquake ever instrumentally recorded. The earthquake was felt throughout the southern hemisphere and caused widespread destruction in Chile. The shaking lasted for approximately 10 minutes and triggered a massive tsunami that devastated coastal communities in Chile, Hawaii, Japan, the Philippines, and other areas in the Pacific Ocean. The earthquake and tsunami caused thousands of deaths and billions of dollars in damage. The event highlighted the immense power of earthquakes and the devastating consequences they can have on human populations and infrastructure. Section 8. The Shanxi Earthquake of 1556, a history of devastation. While the 1960 Chilean earthquake holds the record for the highest magnitude, the earthquake that caused the most deaths occurred in 1556 in Shanxi Province, China. This catastrophic event, known as the 1556 Shanxi earthquake or the Jiajing Great Earthquake, is estimated to have killed approximately 830,000 people, making it the deadliest earthquake in recorded history. The earthquake had an estimated magnitude of 8.0 and caused widespread destruction over a vast area. Many buildings collapsed and landslides were triggered, burying entire villages. The earthquake also caused significant liquefaction, where saturated soil loses its strength and behaves like a liquid, leading to further damage. The Shanxi earthquake serves as a stark reminder of the devastating impact earthquakes can have on densely populated areas. It highlights the importance of understanding earthquake hazards, implementing building codes, and promoting earthquake preparedness measures to reduce the risk of future disasters. Section 9. Waves of destruction. The destructiveness of an earthquake is not solely determined by its magnitude. Other factors, such as the depth of the earthquake, the distance from the epicenter, local soil conditions, and the quality of building construction, also play significant roles. Shallow earthquakes, those that occur closer to the Earth's surface, tend to be more destructive than deeper earthquakes. This is because the seismic waves generated by shallow earthquakes have less distance to travel before reaching the surface, resulting in stronger shaking. Local soil conditions can also amplify the effects of earthquake shaking. Loose, unconsolidated soils tend to amplify seismic waves, leading to more intense ground motion. This phenomenon, known as ground amplification, can cause significant damage to buildings and infrastructure. Section 10. Preparing for the inevitable. While we cannot prevent earthquakes, we can take steps to mitigate their impact and protect ourselves, our communities, and our built environment. Earthquake preparedness involves a combination of individual actions, community planning, and government policies. On an individual level, it is essential to have an emergency plan in place. This plan should include knowing safe places to go during an earthquake, having an emergency kit with essential supplies, and practicing earthquake drills with family members. Communities can prepare for earthquakes by developing and enforcing building codes that ensure structures can withstand earthquake shaking. This includes retrofitting older buildings to make them more resistant to seismic forces. Section 11. Respecting the Earth's power. Earthquakes are a powerful reminder of the dynamic nature of our planet and the forces that shape it. While they can be destructive events, They are also an integral part of the Earth's geological processes. By understanding how earthquakes happen, where they are most likely to occur, and the different types of seismic waves they generate, we can better appreciate the forces at work beneath our feet. Ultimately, earthquake preparedness is about respecting the Earth's power and taking steps to live in harmony with our planet's natural processes. By working together, we can create safer and more resilient communities that can withstand the challenges posed by earthquakes and other natural disasters.